In this video we're going to study performance of different types of airfoil. We're going to receive useful data such as lift coefficient, drag coefficient and so on, and going to plot those graphs. But to do this, first we would have to receive the data for different angles of attack, for different alpha. So we have to go back to our software. So the XFOIL software is the key. Okay, so we are ready for simulation. So let's go to the upper menu. Now let's change the Reynolds number. Now what we can do, we can start data accumulation. We use the command called p.2. Type enter. So the polar, it's called for whatever reason polar. So now at this moment it asks us if we like to have a file name where the data can be stored. So yes, we do. So let's type just file name. The second request is for the dump file. It's not needed. Not sure what's inside of this file. Okay, now we can do what start simulation, but let's initialize the initial condition. Now we're going to start from the scratch, because the XFOIL, it uses the previous solution to compute the next one. So if we like to start a new simulation, it's a good idea to type this command. Now we use the magical command, which is asec, basically sequence of alphas, and we set those, it's going to generate the number of alphas starting from minus let's say 3 degrees to 12 degrees is the step 0.2 degrees, and the simulation is running now. It's very good. Okay, the simulation is ready. At this moment what we can do, we can type p.2 to stop the poly accumulation. Yes, and you can also upload the results if you would like to see actually the actual coefficient. Is the command to plot. So those are the graphs. It's really not intuitive actually what we see here. So I assume that those graphs are okay, but it's not easy to understand what's going on those graphs. So anyways, so the data was saved in the file, and the file 1.txt is here. So let's see what's inside. And here is the data which we have saved. So here's the alpha. We started from minus 3 degrees. Then we have coefficient, lift coefficient, drag coefficient, coefficient of pressure drag, momentum coefficient, and the point where the airflow is separated from the airfoil from 0 to 1. And we have those points going down to 10 degrees. Not 10, but to the degrees. So the same number we have entered with the asec command. Okay, so now let's go to the Python, and in Python we're going to try to plot those graphs, and just to make more sense of this wonderful data we have received. So here's the Python script. I'm using two libraries, NumPy and matplotlib library. Next, I'm loading the data from that file. So this file is the data. I'm going to put this file into this matrix with this function load.txt. Can do it. Can write your own script, but it's simpler just to use this function. So you have to skip your rows. With the description, just start with the numerical data. So So after that we have this matrix, and we split this matrix into the column vectors. So X, CL, CD, and so on. So basically this vector, this is X, CL, CD, and so on. So after that I'm using the function called subplot to plot many graphs. So business as usual, just choose the vector you want to plot. So I'm plotting 6 different graphs. So CL versus CD, CL versus alpha, CL over CD versus alpha, and so on. So why those graphs? And the answer is this web page, airfoil tools, airfoiltools.com. So what they have on this web page, this web resource, is pre-computed results for many different airfoils. So you can choose an airfoil from this menu. And they have the results from the XFOIL. So they have exactly the same file as I do. So I can take a look. So I have a new version 6.99 and they have 6.96. So they have those data for each of those airfoils. And they also plotted the result. So here's the results. So they have those 5 graphs, and to be consistent I decided to plot the same graphs to make sure that my results are not very strange and consistent. So I have should have the same results. And I have done the comparison, so I will show it in a moment. Here is the airfoil I have chosen. So this is airfoil from the airfoil tools webpage. So they have this airfoil and they have the graphs. So they have the data file for this airfoil. Data is the result file, and they have the graphs. So what I did, I copied the profile. Basically copied those numbers. Then I opened this profile in XFOIL software, ran the simulation, and as a result I got this. So this is my result, and this is the airfoil, the same actual airfoil that they have. So the same airfoil, similar graphs, because you can look at the file and you can conclude actually what they did. So you can note the separation between the points and so on. So I did exactly that, and I got similar results. So after plotting this in Python, I can compare. So those are my graphs, and those are graphs from the airfoil tools webpage, and we know that those graphs are similar. Also, what you can do, you can take the file with the results. So this file, copy this file, and then plot it using my Python script. So this is my Python script, and this is the data from airfoil tools. And now you can see that exactly those are the same figures. So there's no differences. Maybe small differences. If you take a look at the results, where is my file? So you'll see that those numbers are slightly different, maybe fraction of a percent. And this happens because the version of the software is a bit different. So the software is older on this web page. My version is newer software. So maybe because of that, but at least you cannot see the difference by your eye. So the difference is really small. And we can conclude that we do have consistent results, and we don't have some strange behavior on the graphs. So at least myself and people from this web page, they come to the same results as I did. So we have the similar results, and meaning that I haven't made any mistakes, which is good because I'm pretty fresh to the subject. So okay, airfoil tools is a good web page and a good start. If you just would like to have some introductory information, for instance, you want to look at some pre-computed results for different airfoils, look at the coefficients and so on, But if you're a bit more ambitious than that and you would like to create your own airfoils and run your own simulation, maybe do it for many different airfoils at once, write a script for this and so on, it's a good idea to use XFOIL directly. So it's XFOIL is not a complicated software. It's pretty simple actually. Like, spend a couple of days to learn all of this, and it's pretty simple. And so when you simulate some new airfoil, what you can do, you can, for instance, change some parameters like number of steps, number of points you're using to simulate this airfoil, and so on. So more flexibility, more power. So this is the way to go for the serious project, but this is also good. And also the graphs, for instance. The graphs here, like this one is the most important graph. Lift coefficient versus drag coefficient is missing one important element. For drag induced by the lift, or lift induced drag. So this line is not present here, so you have to compute it and plot it. So maybe what you can do, you can use this data, just copy paste, and then you can do the same, but again, it's a very small, a bit inconvenient actually. But what I found useful is to look at the different airfoils. So you can choose airfoil from database, and then you have the points for this airfoil, the coordinates for this airfoil, and the coordinates are in the right place, so you can take it as it is and plug it into XFOIL, and you're going to have the results. So this is useful. For instance, you want to like take a fast look at some unknown airfoil, just get the data and you can plot it in XFOIL. So okay, and I would also like to comment on the coefficients in the graph that we have plotted. So those graphs are very interesting graphs, and let's discuss the subject in more details. And to get more details, it's a good idea to read some book on the subject. For instance, this book written by Anderson. It's a good written book, and kind of like it. So in this book, it described how they use those coefficients and how they obtain coefficients and so on. So the main idea is that when we have airfoil in the free stream, what we can do, we can look at the forces acting on each element of this airfoil. So we have 2D airfoil, so that's why we look at only at the airfoil itself, and we ignore the length of this airfoil. And what we do, we look at the pressure acting on this airfoil and the shear stress. So basically the pressure acting normally to the airfoil, and the drag is acting parallel to the element of this airfoil. So we have two forces acting on each element, and what we can do, we can just integrate it along the contour of this airfoil. And as a result, we're going to have two forces. So we're going to have the forces normal, well, they call it normal force, and like in this book, an A force. And as a result, we're going to have the resulting force acting on this airfoil. So the resulting force. But we are interested in a change in coordinate system from the coordinate system connected with this airfoil to the coordinate system connected with the free stream of air. It's meaning that we look basically at the coordinate system in which the plane is moving. So if we represent this vector in terms of its component in this system of coordinates, we're going to have the lift force and drag force. So that's what we need, lift and drag force. Besides, also what we can do, we can compute the moment, because the distributed force which acts on the airfoil creates momentum about some point, and the momentum depends on the position of this point. So XFOIL software, it chooses the point, the location of 1/4 of the chord of this airfoil. so the momentum can be computed as well. So what we have the resulting force, or equivalently we have the lift force, drag force, we have the momentum acting on this airfoil. We can also have the center of the pressure, how it's called, the center of pressure. It's a point along which there is no momentum acting on this airfoil. So we have basically three components: lift, drag, and momentum. So after that, what we can do, we can compute coefficients, lift, drag, and momentum coefficients. Those coefficients are computed in a very simple way. So we divide the lift force by the Q parameter and divide by the area of the wing, where Q is the free stream dynamic pressure. So it defines by this equation where is the density of the air and the free velocity of the air, or the velocity of the plane. So we have those two parameters, we plug them in, and we're going to have the three coefficients: lift, drag, and momentum coefficient. And in our case, because we're working with the 2D foil, so we're not looking at the 3D airfoil, but only on 2D. So the forces actually divide by the length of the wing. So we don't really care about the length, only care about this forces acting on each element. And that's why we go from those big coefficients to small coefficients, where we have the area of the wing replaced by only by the chord length. So the length of the wing is ignored, so we don't have the S here, and we just have the chord length. And in XFOIL it's assumed to be 1, so it goes away. So basically, force divided computed force by XFOIL divided by the free stream dynamic pressure. So this is simple. And just to come back to those big coefficients, if you need them, we can just multiply them by the length of the wing, expressed in the units of chord length. Okay? Yeah, so XFOIL, it gives us drag coefficients of two types: friction drag coefficient, skin friction drag, and the pressure drag. So if we once again look at this airfoil, the pressure always acts normal to the surface, but the wing itself is tilted by the angle of attack, and if we do integration of this force, eventually we're going to have the drag resulted from the projection of the pressure vector on the x component. So this coefficient called CDP, or pressure drag coefficient, and the friction drag coefficient. So basically the friction of the air around the wing results in the friction drag. The XFOIL gives us actually the complete drag coefficient and the pressure drag coefficient. If you look at the graphs, we'll see, like I have the graphs here. So for instance, here is the graph that the XFOIL gives us. So complete drag and drag, pressure drag. And from here we can calculate the friction drag if this component is needed. Okay, so we have the coefficients, and before moving further, I'm going to discuss another coefficient which is useful. It's called induced drag coefficient. If the length of the wing is finite, the vortices are generated at the tips of this wing. So we have the vortex generation happening, and this creates drag. So this effect is noticeable when speed is low and when the alpha angle of attack is big. So, and it's known that this equation defines the induced drag, and this induced drag proportional to the lift coefficient squared divided by PER, where pi is the pi, E is the shape factor, so E is in the range from 0 to 1, and it's approximately approaches unity, approaches 1 when the shape of the wing is elliptic. So for elliptic wing it's almost 1, so we can forget about this. So R is the aspect ratio of the wing, so we divide the length of the wing by the chord of the wing, and that's the aspect ratio. So once again, if we look at this equation, so we would like to have as big as possible this part, so we would like to have E as big as possible, so it approaches 1 when the wing is elliptic, and R has to be as big as possible. So if you are flying at slow speed, for instance, if you have a glider, so then you must have a long wing, so that this drag coefficient is not going to be significant. But if you fly fast, like for example fighter jets or some fast airplanes, so in that case the lift coefficient is going to be small, because you don't need big lift coefficient if you have high speed of the airplane. So the lift coefficient is small, and the drag coefficient, induced drag coefficient, is small as well. And if we plot the total drag, so the total drag is the result of usual drag, which is computed by XFOIL, and lift induced drag. So we get this curve as the function of airplane velocity. And obviously we have the point at which we have the smallest drag, and this is the optimal point for the airplane operation. So this point of minimum drag corresponds to the flight velocity. So if the plane operates at this speed, it operates in the optimal aerodynamic efficiency point, so the optimal position for plane to be in the sky. So how to get this graph? First you have to deduce the equation for the lift coefficient, and if you plug the Q in this equation, so you have the lifting force divided by the Q, which is free stream dynamical pressure given by this equation. So if you plug this, we're going to have the relation between the lift coefficient and the speed of the airplane or the free stream. And from this equation we derive that velocity of the airplane is inversely proportional to the square root of the lift coefficient. And this equation can be plotted, so we have the velocity on the x-axis and we have the lift coefficient on the y-axis. So we have this graph, and we note that when the plane is flying at the maximum speed, at high speed, it does not have to have high lift coefficient. Its small lift coefficient is sufficient because it has lots of air coming onto it, so the force is sufficient to lift the plane. So we have the minimum lift coefficient and a minimum angle of attack at high speed. But if you go at the slow speed, and actually the minimum slow speed called stall speed, so the plane will drop from the sky if you go lower than this speed, it has to have the maximum angle of attack and the maximum lift coefficient. Okay, now we know what those coefficients are, and let's take a look at the results I have plotted. So we have few graphs, and probably the most important graph is a relation between the lift coefficient and alpha angle of attack. So we note it's growing to some point and then it drops. It's almost linear in this range. So this graph is, those graphs are quite typical, and they are similar to many airfoils. So we have the dependence of lift coefficient from alpha. We also have dependence of drag coefficient from alpha. And in this case we have two drag coefficients. I have the total drag, the red line. I have pressure-induced drag. So, and the pressure-induced drag is the total drag minus friction drag. And I also plotted total drag. So I have computed induced drag for some standard wing with some standard shape factor, like say elliptic wing, and the ratio is not very high. So I do see the induced drag plus the total drag. So I have this green curve, and I plotted the total drag on every graph I can, so I can just see what the results are. So this is the second graph we note, and then we have the separation of the flow. So I have the point at which the flow starts to separate. Red line is for the upper surface, blue line is for the bottom surface. And for the ideal airfoil, there is no air separation. So you have one for the blue and one for the and 0 for the red. Actually, it's the opposite is true. So we have 1 for the red and 0 for the blue. So there is no separation. Okay, so those graphs are quite trivial, and then we also have the most important graph. We can plot lift coefficient versus drag coefficient. So we know that we have to have smallest possible drag coefficient, so we have to go to the 0 point. And we would also like to have the lift coefficient in the wide range, so let's say from 0 to the maximum value. So if the wing provides us with the flat line, actually, if it's almost 0 everywhere for every lift coefficient, then this wing is perfect. However, we have to include in our consideration the induced drag. So induced drag is the green line, and induced drag depends on the wing itself. But if you go at a low speed, we're going to have high angle of attack and high lift coefficient. And this lift coefficient is not going to be actually the drag is not going to be the one that we see from the XFOIL simulation. The drag is going to increase dramatically. So basically, because of the finite size of the wing, we're going to have this curve. And this curve is going to be approximately the same for different types of airfoil. So meaning that we don't really care about the high lift coefficient and the curvature of this figure, because eventually the induced drag is going to kill all the beauty of airfoil. So what we actually care is the position here, like a small range for the lift coefficients. So small alphas and small lift coefficient, and in this range we're going to compare the airfoils. So the closer this graph is to the 0, so we have the minimum drag, the better is airfoil. And for the high lifting coefficient, the induced drag is going to play a significant role, and the data is kind of not relevant to the real performance of airplane. Okay, and yes, maybe I will show what I have. Okay, what I have. So here I have results from this web page, airfoil tools, and I have few airfoils. And now we can see that we have few airfoils with different performance. And our task is just to look at the performance in this range. So here it's not going to be relevant because we have like this curve tilted that direction because of the induced drag. But here is the key area where we have to compare those airfoils. So the brown one is probably the best, and this one is the worst. Okay, so we have this, and what else? What else do we have? Yeah, so this graph. We can divide lift coefficient by the drag coefficient and plot this against the alpha. So in a way it's going to show us the optimal performance of the wing because we have the maximum lift with minimal drag. if we care about the lift for whatever reason. Because usually we do have sufficient lift at high speed, it's just enough. But if we would like to have the maximum lift with minimum drag, so we can plot this figure and look at the position at alpha at which this happens. But again, if we introduce the induced drag, this is going to shift significantly, and we're going to have the point which is close to the zero alpha. So we have very small alpha, very small lift coefficient, and at this position the performance of aircraft is optimal. We also can plot momentum and so on. So this is the basic description of the results we obtained. Maybe the next video I'm going to simulate a couple of airfoils.